can start first.
Yeah, hi everyone. My name is Chonghao. So today I'm going to give a joint talk with Kashyap about the end-to-end driving language. Kashyap, if you can say hi to the room. Yeah.
Yeah, hello. Unfortunately, I couldn't be there today, but yeah, looking forward to a good talk.
Yeah, cool. Um, so let's start with a brief introduction of what is end-to-end driving looks like. So as all talks, we need to get things hands-on. Yeah. So now there's many challenges in the driving. So the driving system needs to handle various weather, illumination, and different scenarios. And this is very tackle into a module-based design, since there you will always face so-called corner cases by or say as a long tail questions. And usually, the driving system involves three parts. The perception part will allow you to see what are around in the scenario, basically of the detection in the 3D world. Then you need to have a prediction module. Tells the ego vehicle what are the other vehicles will do in the futures. Planning module that will tell what about the ego vehicle should go in the futures. And basically, there are two ways to do driving system. So one is the so-called classical approach. Another one is called the end-to-end paradigm. The classical approach will be like, okay, we do the perception, prediction, and planning individually, and with some human design patterns linking them together. So the perception and prediction, they will be linked by a bounding boxes, usually a 3D bounding box. So they would work in a 3D manner. And then for the prediction and planning, it will be the ego vehicle or other vehicles trajectory, usually a waypoint in the future. Two modules. But now people are more like, at least the research community are more fancy about the end-to-end paradigms. So like we have and all the modules are connected with the gradient descent rather than the human design patterns to optimize for the final planning tasks. So so now as we define the end-to-end driving system as a raw sensor input, as raw sensor data as the input, and produce a planner or how a low-level control action as the output. Modules can be optimized via gradient descent. That's what we think is looks like. So so what's the advantage of doing this? So there are pretty much advantages like end-to-end manner, like okay, this is simplicity in combining a single model that can be joint training, so you don't need to figure out corner cases at each stage. And also you need to you have the advantages like preventing the cascading errors in module design. So you don't have if there are some errors in the perception task, it won't affect to the planning part. And so finally, the whole system will be directly optimized towards the optimal task, like the self vehicles trajectory prediction. Also, we call it as a planning as for the driving system itself. And so we would like to give briefly introduction of how DriveLM works. We will combine the end-to-end driving system with the visual language models, which is very prevalent in nowadays. So first, let's assume of the driving. Let's take a look at what about the visual language model do in the robotics or in body AI fields. So first of all, many papers nowadays in the robotics field, they use a visual language model to do the low-level control directly with a visual language model. I know this is not very intuitive, because how can a visual language model do output control signal? This is not intuitive by directly mapping the language output into this discretized or number-based action signals. So how people do that is basically like the answer VQA task. The task is about answer and action. Action here I actually refers to the discretized action signals. So when we have some those kind of VQA tasks, then we use this VQA data to tune the with a redesigned tokenizer. This kind of redesigned tokenizer can take handle of the actions that have with the numeric. And then when we have the specific token that predict by the redesign, we de-tokenize those predictive tokens back into actions. So this is very intuitive, but it works really well, as shown in the RT2 or RT series works, like many robotics people are doing real M in action. So so what is good side of this? So this seems to boost the generalization of the model. If you see unseen scenarios before or very complex scenarios with many objects around you, that you can let the VLM itself do the reasoning and to predict the actions. But also it pops out some questions in this paragraph, like is this the right way to open the language toolbox as done in the robotics for the autonomous driving? Because it seems like autonomous driving, it doesn't need the human to interweave with the system. So involving language seems like not necessary. So there are 3 points we think we can answer to these questions, like why we need a language here, because language we think is a generalized and interactive tool for the human to interact with the autonomous driving system. So generalization is about, okay, the vision language model is retraining on the web scale data to be very generalized around the world. What do I mean by generalized? It means that you see many objects that is not familiar it is very familiar on the website. So also there are some regional or global localization requires some kind of explainability about the system. We think that interacting with human through language is a kind of explainability for the human to better understand how the driving system works. And also there are some recent success in the vision language model, like it seems to be very good at reasoning around the world, and then do some visual in context learning. The model itself can understand what it's doing and how to put the vision language model in auto driving system. Like it fits the system well, and then it could help the system to boost some ability in the generalizations. So this is a glance of our work. So maybe we don't have too much time to describe. As we said before, the autonomous driving system has three parts: perception, prediction, and planning, and we do the data annotation for these three tasks, and this will construct our VQA dataset for driving scenarios. And we trained the model on it, and we found that it does have some generalization across different datasets. Like we train on the NAVSIM dataset, and it has some generalization on the Weibo dataset. And we also do this model on Carla, and the Carla things like we have some unseen scenarios, but the model still perform very good in those unseen scenarios. I might go back to the hands-on part. So get in the detail how such a things get evaluated in VQA tasks get evaluated in the driving scenarios. Because this is not the same as the general VQA task, because as you might know, the general VQA tasks, they usually use the MMMU or MMLU things, which are multiple choice. They just need to evaluate if the answer is at a choice level. But in driving scenarios, we have so many objects around you, and those objects will have different behaviors in the future, and all the things are with uncertainty. How do we evaluate such uncertainty, and how do we extract the useful for the later part of the system? So still we will go with the perception, prediction, planning paradigms. So for the perception part, we adopt the general idea of the object detection into the language evaluation part. So say like what the question will be, what the objects in the scenarios, and the GT answer will involve several object description of the objects, and then the predict answer will maybe cover one or more of the objects. But if it doesn't cover all the objects, we will use or a road line or a cedar. These are very common language evaluation tool in the NLP rules. Basically, you can see it as a form of the IOU metrics in the language domain. So if you cover as much as possible of the object described in the class, you will get a higher score. So this is the rough idea how we handle the uncertainty in the perception task. Then we also have some multiple choice design. So this is to ask the model to on the current scenario, like are there barriers in front of the ego vehicle or not? The factual track of the physical world. So this time the things it goes easier because we just have yes and no as the accuracy to measure the performance. And also we have some multiple choice on the future status of ego vehicle or other vehicle. So this time we also do it as a NLP style, like we have the choice to the model, like what is the future state of the ego vehicle at a specific location, and then if the answer the same with the GT one, and then we will give given the correct, then otherwise it is the false answers. And these are for all the previously QA, these are very easy to evaluate. But for the prediction task, because the task we need to evaluate what the other vehicles do in the future simultaneously. At this time, we think this is not as easy as perception of or factual track of the future state. You need to imagine that if the future state of the other vehicle is the same as we use the human annotator to annotate. So at this time, we involve something called the ChatGPT score to evaluate that what is the similarity between the ground truth score and the predicted answers. Yeah, sorry, I go this way. So when we use the ChatGPT scores, given a prompt like we will give a prompt like we'll give you a question and a correct answers. You will need to measure the similarity between these two answers. And I know for now ChatGPT is a not very great tools that fully rely on it on the correctness of the answer. But when we come to it's varying because they have different words and different kind of saying of the same meanings. At this situation, we think that ChatGPT for now is the best tools to use to measure the uncertainty in those like underlying in those answers. And for the final score, we will do a weight sum of all metrics I said before to have a final score of the model. And for now, we think that this kind of rebalancing system is good to evaluate or VQA model or BLM model is having good performance or not in the driver. And Kashyap, I will give the time to you so you can share your screen about how we actually evaluate the what can I say, the trajectory. Yes.
All right. Let me know if there's some problem with the audio or the screen share, but you should currently see a slide from me.
Yeah.
Cool. So yeah, thanks for introducing RivalM, and yeah, I think like the thing I'm going to talk about now is how to evaluate trajectory outputs by these big VLMs. This is extremely challenging because Deva also mentioned it in his talk. There is not really a straightforward way to evaluate driving performance without a simulator, and putting a big vision language model in a simulator is not trivial. So I want to illustrate this with this simple example here. You're in this scenario where I have projected three different trajectories onto the image of a vehicle which is approaching a red light and slowing down. The green trajectory is what most people would think is the best of these three as a behavior to do in this situation. But it turns out that if you measure displacement errors, which is what most benchmarks currently available for using something like a VLM and checking how good it is at driving do, you will see that the red trajectory, which actually is veering off the path and colliding with another vehicle, gets a lower displacement error than the green one and would be considered better. And this is because the point at which the driver slows down in the ground truth, which are these gray dots, is different from the point at which the model being evaluated decides to slow down, leading to displacements between the predictions at specific time steps. And even though both of these trajectories are maybe equally correct, there is a large displacement error between them. So what about simulation? We do really like simulators in our research, and like this has been helpful in developing a lot of models and ideas, and things like NuPlan and Carla are like really great. But the biggest problem I see with simulators is that they're extremely compute hungry. You need to actually provide new input information to your driving model at every time step. And this makes them sort of inaccessible to labs with like small budgets and not much compute resources. There's also, like, to compound the problem of the compute, there's quite high variance between results in simulators often. Like if you retrain your model, you can get scores, like in Carla in particular, on a scale of 1 to 100, you can get a score difference of 20 or 30 points for a different training seed of the exact same model. So this makes it like very hard to make statistically significant comparisons in simulators. So what we use for benchmarking these VLMs is something called non-reactive simulation. I'll go a bit into how exactly this works. So normally in a simulator, you have a vehicle that makes a new prediction at every simulation tick. So this is what I'm going to visualize on the left here in an animation. The green line is the output of a policy which is driving the red car on this road. And you'll see that this green line changes at every particular frame of this animation. The green line is always centered at the ego vehicle and it keeps changing. Um, the this is ideally what you want to do, but um, the difficulty of doing this is that you need to give the policy a new input at every simulation tick, which requires simulating sensor data if you want to evaluate a VLM. So this adds a lot of computational overhead, and also like there's really not that great simulators out there that have like very realistic graphics right now. So what we do instead is make the ego policy non-reactive. Here what you'll see is that in the exact same situation, you have the prediction made by the policy in the very first frame. And we're going to roll out the entire simulation while holding this particular plan static. So we're not going to give the policy a new input at every frame. And so the green line is not going to always be centered at the ego vehicle. You can watch that here. So you can see that the output of the model doesn't change in every simulation frame. You just have a single output and you run your entire simulation of the single output. This is obviously like something that creates quite a lot of differences to the standard reactive simulation. So first of all, you don't observe any states outside your original data distribution. The only ever input your model gets is one of the frames in the data set, which is the first frame in this particular case. But while that makes the task easier for the model also has extra challenges in this setting because it isn't allowed to replan or account for potential problems in its long-term plan, which would be possible in the reactive simulation. Basically, in this setting, once the model has made a prediction over 4 seconds or 8 seconds or whatever your simulation horizon is, it can no longer adapt this prediction and it needs to be much better at long-term planning. So that is like one of the differences of this style of simulation. Um, the other trick we do, which further simplifies and lets like these VLM style models be evaluated, is we make the background traffic non-reactive. I will not go over this in detail because they were mentioned in the previous talk. But the basic idea is that instead of using something like IDM to make other vehicles reactive, you can just let them behave exactly as they did in your original dataset recording. And this leads to weird effects, like you see this blue car driving through the ego vehicle, but it simplifies the simulation environment to a significant extent that it is still useful in creating an interesting benchmark. And now that we have a simulation which is extremely lightweight, so we've removed both the sensor simulation and the traffic simulation aspects, all we need to do is simulate sort of a bird's eye view representation of the ego vehicle. We can actually measure metrics that we care about in the simulation. So we don't need to use displacement errors anymore. We can check if the vehicle under this non-reactive simulation paradigm is colliding with other vehicles, staying on the drivable area, and so on. So I quickly step through like 5 metrics which we currently use. We see if there's a intersection between bounding boxes with the additional check that these intersections are due to error in the ego vehicle. Because like you saw, since we have this non-reactive simulation, we don't want to penalize situations in which another vehicle runs into you from behind, for example. So we need some heuristics for this. We check if we're staying within the drivable area. We kind of have a penalty for near collisions by just making sure the time to colliding is sufficiently large given a projection of the current velocity. We want to make progress, so we don't want to get stuck, and we have a metric for this, and one for having sufficiently low acceleration jerk values. And if we go back to the situation I showed in the very first slide, you can see that like having this diverse set of metrics actually properly captures the different things that are going on with these 3 trajectories in this scene. So you can tell that the orange one is involving a lot of acceleration, so it's not comfortable and goes off the drivable area. The red one has a collision, and the green one is actually a safe driving trajectory. So all these metrics range from 0 to 1, and we have a something that looks complicated, but basically a simple way to aggregate them into a single score, which we call the PDM score, which we use for benchmarking these models. I'm going to skip over this in the interest of time and talk about some of the things we did to also make these tools for benchmarking more accessible. The first was that we found that the data sets you have out there for evaluating or training end-to-end driving models are seldom like possible to actually work with because of their huge size. So NuPlan, for example, has over 20 terabytes of data. We subsampled this to the typical frequency that these end-to-end models use, which already reduces the size a lot. And we released this, it's called OpenScene. We further sort of created like standardized train and test splits by improving the test distribution to filter out very simple situations. And once all of this is done, there's like a very convenient 300 gigabyte download for you to start working with. So I quickly mentioned what we do for this filtering. We observed that in the original NuPlan recordings, and this is true of almost any driving data set out there, some very trivial baselines or heuristics, like in this case, driving straight at a constant velocity and constant heading, actually solve most of the scenarios in the data set really well because most driving data is inherently quite boring. There's not much interesting stuff going on. It's also visualized in these plots here. If you look at the original new plan dataset, these are histograms of where the endpoints of the trajectories are in terms of the X and Y projections. Around like a quarter of the data set, you're standing still, and there is like a drop off of going at higher speeds. But the most interesting thing, and here it's on the log scale, is that around 80% of the data set you're driving straight, and there's very little data, less than 1% of even having a 2 meter shift at the end of the trajectory. So we filtered this using like quite straightforward heuristics. I'll skip the details, but this significantly improves the distribution of turns and the speed distribution over the data set. We also set up this very standard interface with a like task that is well aligned with what state-of-the-art models do today and uses or provides access to inputs that are quite standard for driving algorithms today. And using this, we set up a little leaderboard, and we had a challenge that was also like part of CVPR workshop. We saw that like lots and lots of diverse ideas were submitted to the benchmark because it was like really easy to submit and you don't have this huge simulation compute bottleneck that you have with a typical reactive simulator. The interesting takeaway, or one of the interesting takeaways of the challenge, is that the top solutions and actually many of the solutions started using foundation models. So we had the winner using these big VIT large models, which are trained with like depth-based or object detection objectives. And the second place solution was a vision language model, much like the DriveLM model presented by Chonghao earlier. And using this NAVSIM, which is our non-reactive autonomous vehicle simulator, really simplifies the benchmarking of these models and makes it so that you can do meaningful comparisons between them. So with that, I would like to end my part of the talk. And yeah, thanks for listening. Happy to take questions.
Thank you.